So I think the tools that are used in the EDA community for signal integrity, I think one of the big evolutions that we're seeing is the expansion into not just signal integrity, but power integrity as well. And I think maybe in 3 or 4 years, they're going to expand into EMI. Because I think that these three areas, the distinction between them of what is signal integrity problem, what's a power integrity, what's a EMI, I think those distinctions are blurring, and it's hard to separate the problem into just one of those areas. And I'm going to do a blatant plug for a new journal that I'm the editor of, the Signal Integrity Journal, because we recognize that it's not just signal integrity anymore. It's signal integrity, power integrity, EMI. Sometimes the same engineer is involved in all three of those fields. And so Pat Hindle, who's the editor of Microwave Journal, spun off and created, along with Horizon House, the Signal Integrity Journal that is a holistic approach to these three areas. And I think that's the direction that the EDA community is going in as well, to provide tools that allow you to handle all three of these fields all in one tool. Right now, today, the tools are more specialized for, the EDA tools are more specialized for signal integrity, a little bit of power integrity, separate tools for EMI. There are some of the popular tools like Keysight's ADS, for example, and Mentor's hyperlinks. They are already incorporating power integrity applications inside the tool and integrating the two. So you can look at the coupling between a signal integrity problem and the noise it creates in the power distribution. So that's happening. The next step of integrating EMI, that's, I think, is another couple of years out, but I think that definitely will happen as well. EMI is a complex problem, and part of the problem is that there are so many little pieces of a product that influence the far field radiation. And the calculation of the far fields and how much radiation there is, the calculation of it is incredibly computation intensive. So to some extent, to get started, we need to make a lot of simplifying assumptions. And Einstein used to say, everything should be made as simple as possible, but not too simple. And unfortunately, we're kind of at the range where it's hard to tell what is too simple and what is simple enough to solve. And I think that's one of the challenges currently. But I think in the next few years, those challenges will overcome, and we'll be able to deal with real-world EMI problems in that same tool environment. For the EMI world, the design world at least, a lot of it is build it and test it, or rely on some best design practices, and kind of keep your fingers crossed and hope it passes the test. And then part of the best design practices are a set of kind of design rules. And many of the tools today that are designed to help you in your EMI design or design for EMI are really kind of design rule checkers. And they have a list of a dozen or so known problems that this is going to cause an EMI problem. Make sure the design doesn't have that problem and flag it if there's that effect in there. That's the way most of them are today, and they're pretty effective at doing that sort of thing. When we look at some of the real high-end applications today in the 28 gigabit per second, many of the designs are pushing the limits of what the materials can do. And so you have to be really good at engineering the interconnects to take into account the material properties. No way around that. There's a lot of signal processing that's done in the transmitters and the receivers to compensate for the losses in the interconnects. And so there are fundamental limits to how high a data rate and how large an interconnect we can go. And I think 28 gigabit per second is pushing those limits right now. That's why everybody talks about, and why here at DesignCon, PAM4 is so popular, because it's still at a Nyquist of 14 gigahertz, but you're able to get 4 bits per cycle instead of 2 bits for 28 gigabit. But even doing that has some real significant challenges. So so many of designs are materials limited. And I think we're going to see, we've already seen limits, we've seen these new materials come out that have really, really low loss, and there the limitation in the interconnects is the copper resistance. And the only way around that is using wider lines. And that means thicker dielectric, and that means fewer layers. And so we're at some real fundamental constraint limits in what we can do in the high-end boards. I gave a talk last year about, it was in one of the panels about when's the end of copper and when are we going to go optical. And I think that the next step after we're basically at the limit for boards, and I think the next step before we go to optical is going to be cabled backplanes. All the large connector companies are working on this technology, and I think that's how we can get to 56 gigabit NRZ with cabled backplanes because of the lower copper losses. So the limitation in the circuit boards, fundamentally, there are a lot of different things that can go wrong, but the fundamental limit that you can't get around is the attenuation because of the frequency-dependent loss. And there are two components to that. There's the dielectric, and the dielectric materials that are coming out, Megtron 6, some of the Rogers materials, they have such a low loss that it's almost like air. They're invisible. The loss isn't an issue. The second loss term is what matters, and that's the copper resistance. And the only knob you can tweak to reduce the copper losses is a wider line. That's it. And then you can screw it up even more if you have copper roughness on the surface. And so just to get to the point where the basic copper properties limit you, you have to use really smooth copper. And there are challenges in integrating that into circuit board technology. So fundamentally, it's the copper that's limiting the higher data rates, and because of the resistance of the lines, and that's where we have to look at how wide a line can we engineer, how thick a dielectric is that going to require, how many layers can we fit, and it is a completely different way of thinking about the routing architecture in circuit boards. So as Dave Dunham at Molex says, at 28 gigabits, everything matters. And I am so impressed with what these connector vendors can do in balancing all of these constraints in designing connectors. They have to be mechanically robust. You have to insert a couple hundred pins into the board. You have to be able to solder them. You have to be able to manufacture them, injection mold them. They have to be reliable. They can't corrode. You have to be able to insert and desert. Oh, and by the way, they have to work at 28 gigabits. So it is an incredibly significant engineering feat to engineer the connectors especially, and the packages as well, that these SerDes go into at these high data rates. It's something that everybody has to do everything right in order to operate in the 28 gigabits per second regime. And a lot of designs here at DesignCon are talking about 56 gigabits per second. So as we go up into higher data rates, there are the signal integrity problems because of the losses and attenuations to manage. There are the power integrity issues because now if there's any variation in voltage in the power supplies, that causes jitter on the lines, the data lines, and any jitter contributes to collapse of the eye. And there are EMI problems. More importantly, we're seeing more and more mixed signal designs that have the high data rates as well as having some RF connections for signals going off. And it's the combination of the high-speed digital components, the mixed signals, and these large structures that can contribute to EMI problems. So everything gets harder to do at 28 gigabits, including the EMI issues. Some of us are old enough to remember the good old days when we'd go to Radio Shack and get the Trash 80 at 8 megahertz, and we were so looking forward to the next generation at 16 megahertz. And in those good old days, the interconnects were transparent. There was nobody knew what signal integrity was, right? Because at those data rates, the interconnects, they just kept on doing whatever they're going to do. All you had to care about is connectivity. Somewhere around the 100 megahertz, 100 and 200 megahertz clock frequency, that's when the interconnects became no longer transparent. You had to design signal integrity problems out from the beginning. So the origin of signal integrity problems is really, what's that, like 15, 20 years ago? We've been living with signal integrity. Anything above a couple hundred megahertz has those problems. They've just been getting worse, and the kinds of problems that we deal with are getting more severe and more significant. So signal integrity has been with us for, since the good old days of when we switched to 100 megahertz, and they are only going to grow in importance as we move up this treadmill of higher and higher data rates. So in my class that I teach at University of Colorado in Boulder, one of the processes I teach is starting with best design practices as the starting place to create your design. It's only a starting place, and then you have to do, every design is custom, you have to do your own trade-offs of how to balance the guidelines from the best design practices with what's going to add cost, what's going to add schedule, what's going to add risk. And so you start with the best design practices, and then you have to own them and apply them to those custom designs. as we go to higher and higher data rates, we encounter more and more significant problems that are incorporated into the best design practices. In the old days when interconnects weren't transparent, the best design practices were about reliability. And then we entered the regime where, well, you had to use controlled impedance, and so that became a new best practice. And termination and routing topology. I remember the days when the PCI buses were 33 megahertz, and then they jumped to 66, and then, oh my gosh, 132, and there was a challenge getting 132 megahertz PCI bus working because of the routing topology that they used. To go beyond that, you had to be careful about the routing topology. And so we've been in this constant evolution of best design practices as we go to higher and higher data rates. And now the best design practices for 28 gigabit per second systems means you can't have any stubs that are longer than about 10 mils. That means you have to back drill all the vias and be really careful to get controlled depth in the back drilling. You have to be careful of glass weave skew. You have to use some technique of mitigating the glass skew problem. You have to have as wide traces as you can to control the losses. You have to be careful in the via stack for the packages. So the list of what are the best design practices, it only grows as we go to a higher and higher data rate when we encounter more and more problems to have to avoid. A lot of products today that use this high density interconnects or sequential buildup technology that have micro vias and really fine lines, a lot of those products are very small form factors, and so the distances that you're traveling is really high interconnect density, but the distance we go isn't very large, and so the high attenuation because of those very narrow lines is not much of a problem because the lengths are short. Density is really important, and so it's worth it for those small form factors, mobile products mostly, to use HDI technology. In high-speed products where we're dealing with not just high data rates but also long distances, you cannot route the signal lines in that high interconnect density, very narrow line technology. You need a combination. You need a balance of high density short lines in the microvia and the fine lines, but the long runs that are going from one edge of the board to another that are carrying the 28 or even the 10 or 12 gigabits per second has to be wide lines. And that's where that combination of multi-layer core with the wide lines, thick dielectric, not such high interconnect density for the superhighways, long distances that are carrying the really high-speed signals, that's really important. And for the short interconnects, where a lot of the density is for some of these large FPGAs, large ASICs, the short paths, that's where the HDI technology is really valuable, especially with the ability to do the small BGA footprints on the top surface. So it's other than mobile devices that are inherently really short, it takes a combination, a hybrid approach of the HDI technology on top of the low density, the LDI technology, that would be the superhighways for really high data rate interconnects. So the glass weave effect, or sometimes called the fiber weave effect, is the problem there is you've got the fibers going along one axis in the board, and if a differential pair trace goes along that same direction, if one line in the pair is over more of the glass and the other line is over the resin, then they're going to see a different time delay and you get skew. So the fiber weave skew effect is the problem. There's a lot. We presented a paper here at DesignCon this year and also one last year based on some work my students and I did in our lab in Longmont. And one of the key things that we discovered was that when you report the amount of weave skew effect you have in a board, you think when you're doing the measurement, when you're trying to characterize how bad a problem is this, you think the signal lines are aligned with the glass weave because you think the glass weave is aligned with the edge of the board and the signal lines are aligned with the edge of the board, so the signal lines must be right over the glass weave. What we found in our study, we developed a technique to measure how much glass weave skew is there, quantify how many picoseconds per inch of glass weave skew there is worst case. And what we found is that when you look at many of the boards that are produced, and we had a batch of 50 boards in our study, when you look at them closely under the microscope, you find that even though the signal lines were all routed to the edge, parallel to the edge of the board, the glass weave wasn't always parallel to the signal lines. There was a random rotation between them just because of the manufacturing process. And that random rotation, it sometimes was as much as 2 or 3 degrees of orientation. And if it's more than half a degree, it completely smears out the glass weave problem. Because if the signal is at half a degree to the glass weave, then it doesn't have to travel very far before one line is over glass and then over resin, over glass, and it smears out the effect. And what we found in our study was that we think this is a common problem in the industry. And the reason why the reported glass weave skew that one guy measures over here is different from another guy measures here or here, because they don't look at how aligned are the signal lines to the glass weave. And if it's random alignment, then one board they test, they're going to have really low glass weave skew measurements. Another board they test is going to have large glass weave skew. And if you only look at this board here that had low skew measurements, you think, oh, this glass weave style must give low skew, when in fact it's an artifact of this random misalignment in the manufacturing process. And we think this is a big issue in the industry in how we measure, how we report glass weave skew. And so a lot of the measurements that have been done historically to show, 3313, for example, is spread out glass, and so you don't have to worry about glass weave. In our measurements, when we were careful to make sure the signal lines were aligned to the glass weave axis and weren't rotated, we found 3313 had a lot of glass weave skew in it. Almost as much as 2116, not quite as much as 1078. But if you're careful about knowing exactly what that alignment is, I think it's easy to get a good measurement of the glass weave skew. But if you're not careful of that alignment, your measurement is colored by too much noise and artifact, and you can't trust those measurements. So that's about the characterizing it. The actual mitigating that problem, we think that if you're able to control the fabrication process of the laminate itself and the alignment of the glass weave laminate to the edge of the board, if you can control that and rotate it only a couple degrees, not enough to take up much area in wasted board, but just a little bit of rotation, you can eliminate the glass weave skew problem in the cheapest, lowest cost boards. So we think this problem is solvable by either the fab guys or the laminate guys. We're not sure where the problem starts, but we think it's solvable by those two. And the companies that come forth with this solution first, I think will have a very powerful differentiator to eliminate the glass weave skew problem in their customers' boards. Intel has recommended as one of the mitigations for glass weave skew, rotate the artwork about 15 degrees to the edge of the board. Great, eliminates the problem. You could say, well, wait a minute, why don't we just rotate the artwork 2 degrees? The problem is, when we looked at measurements of boards that we got from a fab vendor, and we looked at the alignment of the glass weave to the signal lines, we found a Gaussian distribution. Standard deviation was about 2 or 3 degrees. That means that some boards are coming out and they're already rotated 3 degrees or 4 degrees, either plus or minus direction. So if you think, oh, I'm just going to rotate my artwork 3 degrees, you may be taking a board that already had a 3-degree rotation in it by random manufacturing variation and now rotating it, so now it's in perfect alignment. And that's partly why 15 degrees works, because it's well outside that normal manufacturing range. But if you're a fab shop and you understand where that random alignment comes from, and you can control it, and you can engineer it and guarantee it to be 2 degrees or 3 degrees, you're not going to waste any real estate by shifting it 2 degrees, and yet you will eliminate the glass weave skew effect. You can use the cheapest glass and the cheapest resin that you want. If you control that orientation, you'll eliminate that problem. And that's why we think it is a really powerful differentiator for the fab company or the laminate company that wants to take advantage of this effect that we've found. When I teach my class at University of Colorado, at the end of the class, at the end of the semester, I give a lecture and talk about my 10 rules and kind of the things to pay attention to as a professional engineer. They're going to be professional engineers. And I end it with 3 guidelines to finish. The first is that it's really important to become your own expert. And that's why they come to these classes. That's why they're engineering students. They want to move up the learning curve. There's no substitute for moving up the learning curve. And I tell them that learning doesn't end when they get their degree and they leave. That learning is a continuous process, and you have to develop the habit of continually learning new things. There's a tremendous amount of information available online. There's my book, of course, that I'm sure many engineers have already seen, this Signal and Power Integrity Simplified. We have a new book I wrote with my co-author Larry Smith that's coming out very soon called Power Integrity Simplified.
I see.
And we have a new journal, Signal Integrity Journal, that has a lot of publications I've written as well as some of my colleagues. It's an online journal, it's free. Anybody can, so you go to signalintegrityjournal.com and anybody can sign up to view it and join the mailing list. So I think these online sources are really valuable. So I think that it's you have to become your own expert. Learning never ends. And the last message I give them is question experts. Don't rely on what experts tell you. Part of the purpose of moving up the learning curve and taking classes and trying things is to become your own expert so that you trust your own judgment, because many of the people that are writing tools, developing the tools that you use, or even writing app notes, they don't know any more signal integrity than you do. And you should, from your experience, develop the confidence that you know what's going on and you're in a position to question what those other self-proclaimed experts do. So I think those are the three most important guidelines I can give other designers to become your own expert, learning never ends, and question authority.